Okay, there we go. So we are starting with electrons, what they do, how they work. They're actually super important in chemistry because they do almost all of the chemistry. So first we're going to talk about electrons in chemistry. Like what I just said is they do all this stuff. Now my pen is of course not working, so that's great. Hang on. Whoa. Oh, it's because it's upside down. I got this, guys. There we go. Okay, so let's fix this. So electrons in chemistry. Why do we care? It's because the electrons do virtually all, no, not all, but almost all, virtually all of the chemical reactions, and they determine the properties of stuff. Okay, so the electrons are really the most important thing having to do with properties, besides mass and stuff, which we've talked about with protons and neutrons, but electrons are going to be super important for us. So the actual study of electrons and things that are super, super tiny is based on quantum theory. So quantum theory, or the study of quantum mechanics and all of that, is really the study of how energy and matter interact on the smallest atomic level. And so this is like the physical chemistry branch of chemistry. So if you've ever heard anybody warn you about PChem being difficult, it's quantum mechanics is what you're doing, and thermodynamics and everything on the very, very small level. So quantum theory is just the study of how energy and matter interact. Again, on the atomic level, interact. On a larger level, that's more of like physics. Atomic level, I was saying physics, so I was writing physics. Okay, so quantum theory is really part of chemistry. It's physical chemistry though, so it's physics plus chemistry. So electrons kind of behave like light. So we're actually going to start with light waves and what those are and how those act. Light is also known as an electromagnetic wave or electromagnetic radiation. Okay, so electromagnetic radiation. Okay, that's important to know. And if you break down the word electromagnetic, we've got electric and magnetic. So these are waves that have an electric component and a magnetic component. So that's what you see over here, how those waves interact. Light just has both of those components, and they both come together to make like what is happening with the light wave. So examples of electromagnetic radiation are, of course, light that we see. So like visible light is what I'm talking about. But if you change certain aspects of the wave, you get things like infrared or UV light. Okay, these are all light waves or electromagnetic radiation. Also X-rays or radio waves. Okay, these are all electromagnetic radiation or light, just in different forms. Okay, so we actually have a lot of principles that will govern these, and we're going to talk about what those are today. So the whole characteristic of a light wave essentially is that they can act as a wave or a particle, wave or particle. So they kind of have characteristics of both. So if you've ever heard the term wave particle duality or the duality of light, that's just because it can act as a wave or it can act as a particle. It has kind of, there we go. It has kind of properties of both. So we're going to talk about what those properties are and how they affect electrons. So light as a wave. So we're going to look at the wave part of how light behaves first. So if you guys ever studied waves, even like in middle school or something like that, you would see a wave like this, and they have different wavelengths. That's going to be one word we need to know. They have different amplitudes, and that has to do with power. That's more of a physics thing. We're not focusing on power. And frequency. So like how many of those peaks pass a point per second. So you do have to know what those mean. So wavelength is represented by this like upside down Y guy called lambda. That's the Greek letter lambda. Okay. And wavelength is just the difference from one peak to another peak. So distance from peak to peak. Okay, and distance we usually measure in meters. So in parentheses, I'm going to put M for meters. Okay, that should be our unit. All right, frequency, on the other hand, its symbol is this little V. It just looks like a V, That's called nu in the Greek alphabet. That's a nu. And it's just like I said, how many of those peaks pass a point per second. So as it's moving through, how many peaks are going to pass this point per second? So number of peaks per second. Okay, so or oscillations per second, that's what the picture says, that's fine as well. These two things, so wavelength and frequency, have an inverse relationship. Okay, an inverse means if one thing gets bigger, the other one gets smaller. So I like this picture down here. I think it shows it really well. The shorter the wavelength, so the distance between one peak and another peak, is going to have a very high frequency. Lots of peaks are going to pass per second or per minute. Okay, so a shorter wavelength is going to have a high frequency. That's inverse. One goes up, the other one goes down. A longer wavelength, so if this is bigger, it's going to have a lower frequency because it's like less peaks are going to pass this point per second as it's moving through. So this has a low frequency. Okay, so these have an inverse relationship. The shorter the wavelength, the higher the frequency. Okay, so if we put all of these types of waves on a chart, this is a very useful chart here. This is called the electromagnetic spectrum. And it actually shows us for different wavelengths and different frequencies, what kind of light waves we are dealing with. So you'll notice we've got frequency here, wavelength here. As frequency goes up, so this goes all the way to 10 to the 24th, wavelength goes down, goes all the way to 10 to the negative 15th. Okay, they are inverse. One goes up, the other goes down. Okay, and so I'm going to point that out here. This is a high frequency. And this is a very short, very low wavelength. Okay, now the other thing on this graph is energy. It says low energy versus high energy. So the higher the frequency, the more energy a wave has as well. Those ones go together and they are opposite of wavelength. Okay, so we can actually see if you know the frequency or you know the wavelength or you know the energy, you can figure out what type of wave it is. So visible light is right here in the middle. And I know you can't see that very well on your, if you printed it off, not in color, but visible light's going to be right there. It's just the small window, the wavelength in nanometers from 750 to 400. Okay, that's just in a different unit. So that's where visible light is. But if it's any higher frequency than 400, you start to get into the UV waves. And UV waves we can't actually see, but those are bad for your skin, right? Too much UV. And the higher frequency you get, they actually turn into X-rays. So X-rays have a higher frequency, shorter wavelength. And then the highest ones that we know or use are gamma rays. So gamma rays are much more penetrating. They have a really high frequency, a really short wavelength. These are really bad for your DNA. They're so short, they can actually get in between your DNA molecules and cause mutations and things. That's why gamma rays are really bad. Okay. Now on the other side, the bigger they are, the less harm that they cause to us. So we got visible light. Then we have infrared. Those are a little bit bigger, slower, or less frequent. Then microwaves. Okay, those are what you literally use in the microwave. They have a lower frequency, a larger wavelength, so we're getting like big waves. Radio waves are actually the biggest ones that we know and use. Excuse me. So radio waves are really big waves. If you look at the size of the wavelength, like right here, this is 10 to the third meters. So that's like that's like a kilometer is the peak to the peak distance. So it's a really big wave. So it has a really low frequency. Okay, so that's kind of how those are related. This little chart here is really helpful in determining the type of waves that we have in different situations. So